Okay, well, continuing on with chapter 6, I believe where we were before is we were about to do example 613 and see what we just did. Oh, the sliding blocks. Yeah, we got done with that. Okay, now we're going to have a sliding crate on a truck, or maybe it's not sliding. That's one of the questions we're going to answer. Here you have a 50-kilogram crate that's resting on the bed of a flatbed truck. The coefficient of kinetic friction is 0.3, and the coefficient of static friction is 0.4. And we want to find the frictional force on the crate when the truck accelerates forward, that is forward relative to the ground, at 2 meters per second squared or 5 meters per second squared. And we can draw ourselves a diagram depending on your level of artistic skill. You can draw the truck if you want to. That's about the best I can do. And on the other hand, what's really important would be the forces on the box. And for that, you can draw a free body diagram where we have the box and we have the weight of the box pressing downward. It said the box has a mass, oops, off screen, of 50 kilograms. And so the weight would be 50 times gravity, or 50 times 9.8, and that's 490 newtons. That's the weight. And pushing back on the box would be the normal force of the bed of the truck pushing up on the box. Since the box is not accelerating up or down, that is not accelerating in the y direction, then we can assume that the magnitude of the normal force is the same as the magnitude of the weight, which would be 490 newtons. And we also, in this case, have the force of the truck pushing forward on the box. And we have the force of friction, which is also pushing forward on the box. And that is a little counterintuitive because we tend to think of the friction as pushing against the direction of motion. Well, this arrow pointing forward here, that is actually the surface of the truck moving forward. But of course, if you think about it, if the box is going to move, the box is going to move backwards relative to the truck. So the direction of potential motion of the box is actually backwards, and therefore the friction is pulling it forward. And that's why we have the friction arrow pointing forward. What are the forces on the crate? Well, we have the weight and the normal forces and the frictional force. We assume the crate at first is not slipping, and therefore we want to use the coefficient of static friction in order to find out what is the maximum force of static friction. And then we can compare the actual force to the maximum force to decide whether the crate is moving or not. If the crate is not slipping, then the acceleration of the crate would be equal to the acceleration of the truck. And looking at the forces in the y direction, because that's the simpler case, we know that there's no acceleration in the y direction because the box is not moving up or down. So the summation of all of the forces in the y direction would be the normal force minus the weight, because normal is up and weight is down. So weight would be negative in this case. And that would be the normal force minus 490 newtons. And that should be equal to the mass times the acceleration in the y direction. The mass is 50 kilograms, and the acceleration in the y direction is, of course, 0. So that means n minus 490 equals 0, and therefore n must be equal to 490, which is basically what we figured out up here already, just logically. Since there's no acceleration in the y direction, then the normal force must be equal to the weight. And since the box is on a level surface, they never actually said in the problem that the flatbed of the truck was level with the ground, but they didn't say otherwise, so you kind of have to assume that the bed of the truck is level. If it were inclined relative to the ground, then that would be different. Okay, now that we have the normal force, we can find out that the maximum amount of static friction on the box would be the coefficient of static friction times the normal force. And the problem told us that the coefficient of static friction is 0.4 and the normal force is 490. So the maximum amount of frictional force for static friction would be 196 newtons. For what's actually going on in part A, the actual force of static friction on the box would be equal to the mass times the acceleration in the y direction. This is the summation of all of the forces in the x direction. The only force in the x direction is the frictional force on the box, and m times a would be 50 kilograms times 2 meters per second squared, because that's the acceleration of the truck in part A. And assuming the box is not slipping, then that would also be the acceleration of the box. And that gives us a static friction force of 100 newtons. And because 100 newtons, the actual static frictional force on the box is less than 196 newtons, which is Fs max, then we can say that yes, it is confirmed the box will not be slipping in part A. And that is the static frictional force. In part B, on the other hand, we have to keep in mind the Fs max value of 196 newtons. The actual static friction force on the box will be 50 kilograms times the acceleration, which, if we assume that the box's acceleration is the same as the truck's, this time that would be 5 meters per second squared, and that's 250 newtons. In this case, the actual static frictional force is greater than the maximum static frictional force. So that means the box is not static, it's not sitting still, it does slip. And that means that you have to use the coefficient of kinetic friction instead. So the force of kinetic friction would be the coefficient of kinetic friction times the normal force, and that would be 0.3 times the normal force, which is still 490, and that would give us 147 newtons. Okay. And let's see, find the frictional force. That's what the question was asking for, the frictional force on the box. If you wanted to find the acceleration of the crate relative to the ground, then all you have to do is find from the equation the net force in the x direction is equal to the mass times the acceleration in the x direction. You can rearrange that to find the acceleration in the x direction. That's the net force in the x direction divided by the mass, and that would be 147 newtons divided by 50 kilograms, and that's 2.94 meters per second squared. That's the acceleration of the box relative to the ground. Notice that the acceleration of the crate or the box relative to the ground is actually less than the acceleration of the truck relative to the ground. So the crate's acceleration is actually backwards relative to the truck. In other words, from the point of view of the truck, the crate appears to be moving backwards. And you can think of that also from an inertial point of view. In order to get the box moving, you have to overcome a certain inertia. If the truck kind of moves too fast, the box will lose its grip. But because of the box's inertia, it will tend to stay where it is while the truck moves out from under it. And the net effect is the truck's moving forward, the box is basically staying where it is, and the box appears to be moving backwards relative to the truck. So the acceleration, if you want a number for it, the acceleration of the crate relative to the truck would be just the acceleration of the crate relative to the ground minus the acceleration of the truck relative to the ground. That would be 2.94 minus 5, or negative 2.06 meters per second, squared. So that would be the acceleration of the box relative to the truck. And notice it does come out negative. Okay, that was interesting. There is also possibility for working on inclined planes. As before I mentioned that the bed of the truck we kind of have to assume is level to the ground because they didn't give us any information otherwise. But basically, if it's not level to the ground, they'd have to tell us what the angle is. And that comes into play in this next example, which is about a snowboarder accelerating downhill. You've got a snowboarder that's going downhill on a slope of 13 degrees. So there's your angle. And the coefficient of kinetic friction is 0.20 between the board and the snow. And so what is the snowboarder's acceleration? Interestingly enough, in this case, you might assume that you need to know the snowboarder's mass. But actually you don't, because of the way that this can be worked out. I mean, it would be nice if you did know the snowboarder's mass. That would make it somewhat easier, but you don't have to know it. So what we do know is that the force of kinetic friction will be equal to the coefficient of kinetic friction times the normal force. We know that we can draw the free body diagram where we have a gradual slope, a 13-degree slope relative to the horizontal. We would want to orient the axes so that one of the axes, the x-axis would be the more obvious one, goes along the slope, and the y-axis would be perpendicular to that. We have the snowboarder here with it. Basically, the snowboarder's weight has a component in the x direction and a component in the y direction. The snowboarder's actual weight is pushing down toward the center of the earth, but what we can really care about would be the x component and the y component. So I'm going to cross out what I just drew there, and we'll go with the x and y components. The y component of the weight is what is balanced out by the normal force, which is 180 degrees opposite the y component of the weight. And also there's the frictional force, which is pulling backwards on the snowboarder, sort of trying to prevent him from going down the hill. Okay, so we have the x component of the weight. That's going to be mg sine of 13 degrees. Remember, because this is on an incline, the sine and cosine switch. The x component is normally cosine and the y component is normally sine. But if it's on an incline, it goes the other way. So the x component of the weight, mass times gravity times the sine of 13 degrees. The y component of the weight would be the mass times gravity times cosine of 13 degrees. And the normal force would be equal to, the y component of the weight. And also, we know that acceleration in the y direction is 0. In order to look at this situation, we're going to want to look at the sum total of the forces in both the x and y directions. And so we can lay out the total of all of the forces in the x direction would be equal to the mass of the snowboarder and the board times the acceleration in the x direction. The summation of all of the forces in the x direction would just be the weight in the x direction, that is the x component of the weight, which is what's pulling the snowboarder down the hill, minus the friction in the x direction, which is trying to pull the snowboarder back up the hill. So that is the total of all of the forces in the x direction, and that would be equal to the mass times the acceleration in the x direction. The weight is equal to mg, that is the x component of the weight, is mass times gravity times the sine of the angle. I'll call it theta for now. We may or may not need to put in the number later. And the frictional force in the x direction is going to be the coefficient of kinetic friction times the normal force. And all of that should be equal to mass times acceleration in the x direction. But the one catch here is we don't know what the normal force is. So we'll set that aside for a moment and go over here where we have the summation of all of the forces in the y direction should be equal to the mass times the acceleration in the y direction. The sum total of all of the forces in the y direction should be the normal force, which is going upward, minus the y component of the weight, which is going downward. And that should be equal to mass times acceleration in the y direction. The normal force, again, we don't know what it is, so we're just going to call it n minus mg cosine theta. That's what the x or y component of the weight is, mg cosine theta, should be equal to mass times the acceleration of the y direction is 0. Because the skier or the snowboarder is not rising or falling, so there's no acceleration in the y direction. And so that overall is equal to 0. So n minus mg cosine theta is 0. And what that means is that n is equal to mg cosine theta. Now that we know what n is, we can come back over here and insert it for n on this side. So now we have what we had before anyway was mg sine theta minus coefficient of kinetic friction times the normal force equals max. Well, substituting in for n, what we now have is mg sine theta minus mu sub k times mg cosine theta equals max. Well, obviously, we want to solve for ax, the acceleration in the x direction. So we divide everything by m. And what we notice is that there is an m in each of the terms in the numerator. So that crosses out with the m on the bottom. And there's, so basically the denominator goes away. And both of the m's in the numerator go away also. Also, you notice there's a g in each of the terms in the numerator, so you can factor that out if you want. So that would be g times sine theta minus mu sub k cosine theta equals a sub x. We know what g is. That's 9.8 meters per second squared. And that's going to be times the sine of 13 degrees minus mu sub k, which they told us up here was 0.2, times cosine of 13 degrees should be equal to ax. So that's 9.8 times 0.225 minus 0.20 times 0.974, and that comes out to 0.296 meters per second squared. That would be the acceleration in the x direction, which is down the slope. It's a positive number, so it's going down the slope. And it's not a very big acceleration, actually. So if, largely because the angle of the hill is not very large. It's only a 13-degree slope. So you normally wouldn't expect to have a very big acceleration going down a gradual slope like that. If the angle of the slope were much smaller, then there might be no acceleration at all, or the acceleration might even be negative. And the same is true if the coefficient of kinetic friction were much bigger than it is, then the acceleration might end up being 0 or even negative. If it were negative, that would mean that the ski boarder would actually be slowing down rather than speeding up. Okay. All right. The last few videos have been running long, so I'm going to actually cut this one off a little early. And so I'll be back for the second segment in just a moment.